Hey guys, welcome back. Today we're going to talk about adding custom attribute sets to your per project gameplay ability system. Let's get started. Attribute sets contain attributes that gameplay effects can modify. Only put attributes into your attribute set if they need to be modified by gameplay effects, since attributes are more expensive than replicated properties. In the Hub World MMO, our base character stats, strength, agility, and constitution are not put in a gameplay ability attribute set. We're using them as base stats, and so we only put the derived stats into the attribute set system, and this saves us having to pay the extra cost for those three base stats. Actors can have one or more attribute sets. Currently in the Hub World MMO, we only have one combat attribute sets, but in the future we'll be adding more and we can mix and match them per actor. We'll see how important this is a bit later, but attributes in attribute sets can be replicated to all clients or only to owning clients, and this has a large performance cost difference. Okay, this is super important. This is the most important thing in trying to understand multiplayer programming in Unreal Engine. You're going to want to watch this multiple times. If you get this and fully understand this, multiplayer programming in Unreal Engine will be easy. If you don't get this, you're never going to figure it out. This is the most important thing. Here we go. Network, role, and authority. There isn't just client and server. It's more complicated than that. There are three roles: authority, which is the server, autonomous proxy, which is what I often call owning client, and simulated proxy, which I often call proxy client. Now, here is the description from the Unreal Engine documentation. It is confusing and it's potentially misleading, and I'm going to show you why and how you can understand it so that you don't get misled. But I'm going to read their documentation first here for those three types. So they have authority. The actor is authoritative and replicates its information to remote proxies of it on other machines. As long as this is thought of as the server, this is fine. There's no issue. The next two is where the issue is. Simulated proxy. The actor is a remote proxy that is controlled entirely by an authoritative actor on another machine. Most actors in a network game, like pickups, projectiles, or interactive objects, will appear as simulated proxies on remote clients. So the problem here is that they're potentially misleading you to think that simulated proxy has something to do with pickups, projectiles, or interactive objects, and that's really not. That's too simple. That's not exactly what's going on here. And then the next one is autonomous proxy, which is the actor is a remote proxy that is capable of performing some functions locally, but receives corrections from an authoritative actor. That's fine. Autonomous proxy is usually reserved for actors under the direct control of a player, like pawns. So this is potentially misleading in that it makes you think that if it's a pawn or a character or something that inherits from a pawn, it's always going to be an autonomous proxy. That is not correct. That is not how it works. Let's take a look at how it actually works. This is the most important part. Okay, I have created a diagram here of a pocket of relevancy on an Unreal Engine server and three clients. Okay, it's a pocket of relevancy because technically this could happen multiple times throughout the server as players get together close into one area. So the way to think of what I've diagrammed here is that player 1, player 2, and player 3 are standing next to each other. There's also this player 4 here that is not relevant. Not close enough to player 1, not close enough to player 2, not close enough to player 3. Doesn't make it into this relevancy system, this pocket of relevancy. Okay, so here's what we have. We have player 1's character, player 2's character, and player 3's character on the server. Their mode is authority. Okay? These are the authority. They're sitting there on the server. This is a character, this is a character, this is a character for player 1, for player 2, and for player 3, and they have authority. Now we have 3 game clients, player 1, player 2, player 3. Player 1 also has 3 characters, player 2 also has 3 characters, and player 3 also has 3 characters, for a total of 12 relevant characters. 3 characters over 3 clients plus the server ends up as 12 characters. Okay, so there's 12 characters we have to deal with when there's 3 players that are relevant. Notice that for player 1's character on player 1's client, player 1's character is autonomous mode on the client. This is the most important thing, okay? So player 1's character is autonomous on player 1's client. Player 2's character is autonomous on player 2's client. Player 3's character is autonomous on player 3's client. But player 1 also has player 2's character and player 3's character in simulated proxy mode. Player 2 has player 1 and player 3's character in simulated proxy mode. Player 3 has player 1 and player 2's character in simulated proxy mode. You see the pattern? The pattern is that your own character is in autonomous mode, but other players' characters are in simulated. This is super important. It changes how everything works, and it's going to be very important to us when building our attribute sets for the gameplay ability system. Now, you will also notice that I have lines to the server. These lines are actor channels. This is how replication happens. Notice that for simulated proxies, they only go one way. Simulated proxies cannot push data back up. They do not have access to a player controller, and therefore they cannot make RPCs. Player 1 can make RPCs up to the server by using its attached player controller. That is because the autonomous player character has a player controller. The simulated proxy player characters do not have player controllers. Does that make sense? Good. So what we just saw is that the number of simulated proxies grows exponentially relative to the number of relevant players. The number of simulated proxies in a relevant system is equal to n times n plus 1, n times n minus 1 plus n. The total number of characters in a relevant system is equal to n squared plus n. This exponential relationship between number of players and number of characters is why scaling beyond 100 players per server becomes very difficult. It's why reaching 100 players in itself is difficult. Let's take a look at the graph so that we can see this relationship. On the left axis, I have number of characters. These are 1,000 in each of these lines. 1,000, 2,000, 3,000, 4,000, 5,000, all the way up to 10,000. On the bottom axis, I have number of players. Okay, so we can see here that slightly past 30 players, the system will have over 1,000 characters. Does that make sense? Remember what we saw before, how it scaled exponentially, because every client had to have everyone else's character plus their own in the relevant system. By the time we get to 50 players, we're over 2,500 characters. At 70 players, we're almost 5,000. At 90 players, we're over 8,000 characters. 90 players, 8,000 characters. That's crazy. And by 100 players, we're nearly or actually, I think we're past 10,000. Yeah, we're past 10,000 characters at 100. So this, because of how this scaling works, if you were to try to scale this out to, 1,000 players per server, you end up with close to 1 million characters. 1 million characters is a lot for only 1,000 players. So this exponential nature of this relationship is why it's so difficult to scale to more players, because every additional player costs exponentially more than the player before it. Now, this is assuming that all of the players are relevant. If they're not all relevant to each other, it doesn't scale this bad. What becomes difficult, though, is trying to stop players in a fully open system from converging in one place and thereby all becoming relevant and creating lag and crashing the server. One additional thing we have to talk about here, because we didn't set it in the previous video, is gameplay effect replication mode. So we're going to set this in our begin play based on our character usage. There are 3 modes: full, mixed, and minimal. And the recommendation from Epic is that full is for single player games, mixed is for player controlled characters in multiplayer games, and minimal is for AI controlled characters in multiplayer games. So we'll be setting our gas player character to mixed, and we'll be setting our AI character to minimal. The project we have here is the one that we started last week. In last week's video, that video was called Per Project Gameplay Ability System. And so we're starting with that project, and we're going to add our attribute set to it. So the first thing that we need to do is that you'll see here that we have a HWA gas character, right? But we need to add a player character. So we're going to go here and we'll create a new class. And we're going to inherit from HW gas character. But this one is going to be called HW gas player character. And then we can have our blueprint inherit from that. So we'll create that. And we'll reload all and stop debugging. Now we need to set our gameplay effect replication mode to mixed for this player character. And so we're going to have to do that in the constructor. We'll add the constructor. And now we'll set the replication mode. We're setting it to mixed because this is the player character. Now we're going to add our combat attribute set. First, we're going to create a base attribute set that all of our other attribute sets can inherit from so that we don't have to duplicate the code. We're going to call it HW attribute set. We'll go to Tools, New C++ class. We'll inherit from attribute set. And we'll call this HW for Hub World, HW attribute set. Create the class. We'll stop debugging. We're going to paste in the first piece of code here. What we've got some forward declares. This is to stop circular references. So we have forward declares for ability system component, object, and world, which we'll be using down here in a minute. But we've got this attribute accessors, and this is built into Unreal Engine. These gameplay attribute property getter, value setter, and value emitter. And we're just saying, hey, create one that we can call, and it will create all of them. We're just trying to minimize the amount of code that we have to type per attribute. And so that's what we're doing here with this attribute accessors. When we use this macro, it's just going to call all the rest of them, which each of those have underlying code as well. Our base class is going to have two built-in methods that will be reusable. One is to get world, to get a pointer to the U world, and then this other one is to get the HW ability system component. Things that our attribute sets are going to have to often use. We're going to have nice convenience methods here for those. Now we'll go to the CPP file and add the definitions. So we're going to paste in our definitions. You can see here we've got get world, where we make a call here to get outer, and then we use that outer to get world. And then we've got another one here that's going to take our owning ability system component and cast it to our HW ability system component, so we have a nice pointer to use. Now that we've created our base HW attribute set, we're going to go in and create the combat attribute set that inherits from it. Tools, new C++ class will inherit from HW attribute set. And we're going to call the new one HW combat attribute set, and we'll create the class. Reload and stop debugging. We'll add our declaration of our constructor, and then we'll add the definition for the constructor. But now we need to add our attributes. And I don't like to type them. I'm lazy. So I wrote an Excel script to be able to generate them for us. This Excel document is in the video description. There's a link to it. And we're going to open that now. So what I have here is I have a list of the attributes that we want to add. So you can type your attributes one row per. And then if you need it to hide from modifiers, this basically just means that a gameplay effect can't directly modify it. Health is the only one that we do that with currently. And so we're going to set that to yes. And that's the only valid value in this column. Otherwise, just leave it blank. And then we need to set some values here. The path to save to. So it's going to L Unreal Projects at gas01, which is the root of this project. And then we have, yes, we want a BP getter, a BP setter, and a BP init. That macro we saw earlier where it had the accessors, those were C++ only. They weren't usable from BP. So we had to add additional code if we want to access them from BP, which we're going to use. There's enough cases where I think that we would want to do that. We set our BP prefix, so they're going to start with HW. So it's going to be like HW get, HW set, HW init. We give it the name of our attribute set class, which is U HW combat attribute set. If you're wondering about the U, it's because it's a U object. When you make HW combat attribute set, Epic appends the U in front of it. So we need that U. And then our BP category. This is just the category, the nice name that it shows up under as a category in BPs, and they're going to show up under combat attributes. So what we do is first we have to, there's a security warning here, and we have to trust the content. There's nothing bad in it. You can go into the code and view it. It basically just loops through these rows, inserts the values into a snippet of code, and then outputs a text file. So we will select starting in A2 down to B18, and we will hit Run Script Builder. And it will create a script.txt file. So it just generated this. You can see it's wrapped in this begin auto-generated attributes down to N. We're just going to hit Control-A, Control-C, grab all of that, and then we're going to come back to our project, and we're going to paste that in. And so hundreds and hundreds of lines there we did not have to type. So that generated our attributes for us. We are not done yet, though. There's a few more things that we have to do. So I'm going to scroll all the way down to the bottom. So we did not generate our damage and healing transients. They're a little bit different. The code looks a little bit different. I decided not to add it into the Excel spreadsheet, so we're going to paste that here. So here we have our damage transient and our healing transient. These are values that we can use to change health because health is not directly accessible to gameplay effects. So instead, you modify damage to decrease health. You modify the healing to increase health, and that's what we're going to be using. Now let's take a look at one of these attributes. So we'll look at the last one here, defense, and you'll see that we have an F gameplay attribute data. This contains a base value and a current value. This is a structure. And we have defense here, but you can see that it says replicated using on-rep defense, which is defined here. But because this is a replicated value, replicated property, we need to add it to lifetime replicated props. So we're going to add that now in the CPP file. We're going to go to our CPP file and we're going to paste this in. This is the get lifetime replicated props. And what this is going to do here is this is going to set up the replication conditions for each of the properties. And so we talked about earlier about that some attributes may only be replicated to the owning client, which is the autonomous proxy, while other ones will be replicated to all proxies. And so if we take a look here at what we have, you will see that our health and our max health have condition none. So the idea here is that there's no condition on these, there's no filter. They're going to replicate to all relevant clients. And because of that, we'll be able to use health and max health in a health bar that shows over enemies. And that's the reason that we had to do that. But for now, we're taking all these other things, health regen rate, energy, max energy, all of these different things. Looks like there's an error on this one. Used twice. Stamina, max stamina, agility, constitution, all these other ones. We don't need proxies to know that. We don't need simulated proxies to know that, right? And so we put the condition underscore owner only, which means that only the owning client or the autonomous proxy is going to get those values replicated. So by doing this, we've significantly reduced all of this replication. Now you can see here that it's not happy about some of this here. And so we're going to actually paste. We're going to paste in some additional includes here. Some of them we needed right now, like the Unreal Network for this get lifetime replicated props, ability system component, the gameplay tag container, this effects stuff, tags module. We won't need that until next week's video or the week after. Yeah, but I'm gonna just add them now, paste them all in. They'll be here ready for us. We're also missing a few includes from our combat attributes set, so we're gonna paste those in. And we'll give it a try. Remember that we created a new class called HW Gas Player Character, but we haven't changed our blueprint to inherit from it. So let's do that now. We'll go into our BP third person character, and we're going to go to File, Reparent Blueprint, HW Gas Player Character. At this point, we don't have any gameplay effects that are being applied. We also have not done our pre and post gameplay effect execute, which we will do next week. And so at this point, we can't actually see it working yet. So next week we will do that, and we will be able to see that working. If you have any questions related to this video, please leave your questions in the comments section. The Open World server and Hub World MMO Discord link is in the video description if you want to discuss something in this video further. Like and subscribe to be notified of future videos and to help with the algorithm. Until next time, have a good one.